everyone. Thanks for coming and sticking around. It was an awesome presentation that we had before. We're all working along a similar axis here of talking about transformer models, generative AI, and all that in whole, especially the embedding space, as I'll also explore later on in my slides here. It's just a really hot space, and I'm really excited to bring you responsible Gen AI for computer vision, seeing more of what our model sees and not just what we see. So feel free to drop more questions into the Q&A. I'll be sure to clean them out, as well as I have a quick demo at the end to show everyone exactly what I'm talking about here. So it's no surprise to everyone here that there's been a new generation of models coming out, especially how it's affecting both language as well as computer vision. Rocketed onto the scene with ChatGPT, and it's only been accelerating even faster. It's really being marketed as a tool for all solutions, right? The way you apply these transformers and diffusion models is not a matter of it's not strong enough. It's just a matter of can you find the right way to apply these tools to your problem? It's almost like you can imagine that the plane is on the runway, ready to take off. You just have to wait for the right pilot to take off and pilot that plane. It's how you leverage these tools and these models for you to be able to get the most out of them. Another thing that's coinciding with this, and this is nothing new, is that not all data is perfect, obviously, right? Whether it's low sample size, low variety, or just poor quality data in general, has been an obstacle for computer vision for decades. And up until now, we've been kind of limited either by the resources, sometimes there's a literal resources of going out and taking pictures, for instance, compute in order to calculate these very complex transformations or augmentations onto our data set, or really just the understanding of the right way to make poor quality data high quality data, right? And the best way we can kind of dress up or put makeup or whatever kind of term you want to use on your data set to make it prettier than it was before and train your models to higher performance has also been improving over the years. And that's fine. As we see, there's so many new image augmentation techniques coming out, and especially with Gen AI, it's kind of shaken up the field. Because previously, we've only been able to do things like flipping around pictures, as we'll see in a second. But now with diffusion models and Gen AI models that are able to in-paint your pictures or create whole new images, your new limitations are kind of more on your creativity and your curation, which is a very specific word there that we're using. It's a matter of how much you can get to the right images that you're trying to bolster your data set with, but also being careful enough that you're not actually going to hurt yourself in the process. So we're going to look at some traditional synthetic data sets as well as some other things. So we're going to start from what we have been doing in the past, right? As early as a year or two ago, before Gen AI was exploding onto the scene in computer vision. What were we doing? Well, we were taking synthetic data sets that were coming from some type of 3D engine, which this kind of flexibility gives you unlimited control of the 3D scene. You'll be able to get insightful metadata because you have control. You can see all the inputs. You're able to say things like the type of weather, the daytime, all these kind of assets, whatever assets you want to drop into there. It's very highly customizable and very powerful in order to generate this synthetic data. If it looks like it's GTA, that's because it is GTA. This is one of the most popular ways to generate synthetic data is by using video games like Grand Theft Auto. And there's many problems that comes along with this. One is that multiple points of input lead to multiple points of failure. And you can kind of see here on my right, this is from a survey that's summarizing the best practices to use whenever you're using synthetic data sets in this old classical form, relying on a video game engine or 3D engine to generate your images. The idea here is that if I'm doing something like vehicle detection in my video game, which I have now full control over the space, I don't need to be playing it to get my samples. I can swing cameras around during different weather conditions, different traffic conditions, different types of cars, and all the popular cars I'm interested in have been modeled into Grand Theft Auto, and I can now capture all the different synthetic data points that I like in order to get train my model and bolster my data set with this synthetic data. The issue with this is it requires a lot of skills that many computer vision engineers don't have, whether it's cracking video games to get to the point where you can move these camera angles around, knowing all the different lighting conditions, camera conditions, weather conditions, and how to tweak all these variables, as well as it's just a very high barrier of entry or requires a large team of people to do this. I can speak by my own personal experience, was a vehicle detection problem. And we had a whole team built around this. And I mentioned to the person whose job it was to take the pictures in the video game engine, that we need to have all angles of the car in the picture, so that way we can make sure that our model, whether it's really high up or really close to the car, is always going to detect that there's a car there. What happened was that half of my pictures came in like this on my bottom left, because including all the angles included all the angles on the bottom of the car. This was not obviously communicated well enough to him, and it just shows how the problem can be complex, where his knowledge of computer vision was not super high. So he did not know that bottom pictures of the car, for instance, are not meaningful to me. As I hope that most of the cars I'm detecting are not completely upside down, right? So just goes to show how it's a very complex. The data is not even going to be super robust. It's very hard to grab it, but once you do, it can be very powerful. It's just really hard to get there. The other alternative here is now we move along the pipeline of somewhere in between Gen AI and classical is image augmentation. Maybe you're familiar with this. We're not going to spend too much time on it, but this is kind of what traditional computer vision has been doing for, as a stopgap between poor quality data or low quality samples or low number of samples in your data set, has been low level transformations of the image, such as flipping, cropping, medium blur, contrast. You can see here on the bottom right, mosaicing, which was like a huge breakthrough in YOLO v4 whenever it came out, and that you got all this extra performance out of your model by cropping 4 object detection samples together. The problem with this is it kind of loses the context, right? You're not really showing the model anything that much newer. You're just showing the existing data in a different style, but not really capturing what it means to change to the high quality or the high level features of the picture, right? You can imagine if I want to say, change my black cars in my data set to white cars because I don't have enough white cars in my data set, then I can't really explain this, or I can't really solve this problem through traditional image augmentation. Likewise, if your quality of your data was always poor, for instance, if you had very noisy or blurry pictures like this on the bottom right, well, you also can't really fix that with traditional image augmentation. If the quality of the sample is poor, when you augment it and train your model, it's always going to be poor, right? So this is another thing to consider of how do we close these gaps? How do we explain to some kind of method to change the pictures that way our data set is more robust, it's more diverse. That way our model trains on more types of images. That way we get to a higher model performance. And the answer here is going to be generative data sets, right? Or seems to be the answer. With generative data sets, we see unprecedented amount of creative control. And it's really easy and it's really cheap as well. It's really easy to prototype different problems, prompt these kind of things. You can go over to any type of model serving website, pick your favorite off-the-shelf text-to-image model, or if it's an in-painting model, and you can start prototyping, bolstering your data set using completely synthetic data, right? For instance, butterflies. If I need to add more monarch butterflies to my data set, as I didn't have enough whenever I was collecting them, or maybe you're working with things like endangered species is a classic one, or fossils I've heard before, where there's only really a set amount of these in the wild. So unless we're going to try to overfit to this problem by, just flipping our pictures around from the 4 or 5 fossils that I have, well, we can actually use generative data sets and generative AI to help bolster our data set to create samples that don't exist. This way, our model sees new things for the first time. However, there's a lot of caveats that can come with this, that we need to navigate this progress thoughtfully, right? A lot of these Gen AI models, as we've seen in the news and stuff, have been known to have biases, right? And how are my prompts, or how are the problems I'm going to work on, are they going to run into these biases? Are there ways and steps I can take to mitigate these kind of risks? As well as data privacy. If you're doing things like in-painting, or if you're working with specific types of data sets, we have to make sure we're not passing certain private details along to some of these model providers. Things like license plates, faces, and more can be something that we don't want to be doing potentially. Is there a way to get rid of this information before we kind of get into this process? And it's just important, especially in the stage that we are now, that we learn and understand the gaps in Gen AI, so that we're always applying it to our models and our projects thoughtfully. A couple examples on how this can happen. One is that artifacts are added or removed from your images after passing them into some type of Gen AI or artificial intelligence model. For instance, we have these CAT scans or X-rays on the bottom left. And one of the most popular ways to deal with noise in images today is to use a super resolution model, right? I can now take my existing, standard def or high def image, I can actually upscale that to 4K or something better. And if there's a lot of noise or blurriness in my image, I can actually remove some of that using these super resolution models. The issues with this is that sometimes they're not always trained or not trained perfectly on the domain you're using them for. For instance, if you use a super resolution model that was trained on restoring images with blurry pictures or noise in them, and then I try to apply this to medical images, there's actually cases where we find that artifacts are being added and removed into these X-rays because as you're trying to fill the gaps with noise and blurriness, you're actually going to be removing or adding artificial tumors or things like that along that line, right? And so, instead of actually helping aid the doctor now in their diagnoses, you're actually hurting them by taking away some of the key things you're looking for. So it's one type of way. The other one that we see even more prevalent is the data drift problem here. Of even though you're bolstering your images with these new GenAI models, whether if you're in-painting in new weather or you're going to be creating completely new synthetic data sets, the data drift is a serious problem because if the data looks the same for us, but the model doesn't see the same type of data, then we're not going to be reaching the same problem here. And you can kind of see this in my toy plot down here. But by adding these new synthetic data in, if you're drifting your data set distribution towards more synthetic data, it no longer matches the distribution or the features of your existing data, then you're altering the hidden patterns and you're not really going to be ultimately helping your model train at the end of the day. You're only going to be hurting it as it's going to start overfitting or skewing towards synthetic data, which we're not going to be actually seeing in the real world, right? So we want to make sure that our synthetic data that we're generating is always matching the real world distribution as closely as possible. This is a problem I've kind of been tracking over the last 2 or 3 years, and it still plays the same today as it did 2 years ago. So I'm going to hop over to a live demo. I need to hide my bar so I can pick my demo. So we're going to look at butterflies, as I mentioned before. Here I have a butterfly data set of around 12,600 butterflies. I have 90 different butterfly species here. We could scroll through. And using FiftyOne here, we can even generate embeddings for our butterflies and have them side by side. So we can see all the different butterflies colored by their label types on the right, as well as I see all the butterflies correspond to the left. And now before we get to the part we're going to show here, I'm going to go over here and filter my butterflies by personally my favorite butterfly type, which is the monarch butterfly. Now there's something I've been alluding to here, and it's going to be a fun little test for us. Is there any way, as I scroll through here, can you, as a person looking through this data set, do any of these butterflies jump out to you as synthetic data? I can clearly look as I scroll through these, that one's synthetic versus that one's not. Some of them, maybe, if you're looking close enough, this one always jumps out to me. But some of them, I've hidden 5 pictures in here that are not real butterflies. I've generated them using various different models, whether they're DALL-E 3, Stable Diffusion 3, or other models. But I've hidden them in here. And the point I'm making here is how do I know, given this problem, that my data is not drifting, that my synthetic data matches my existing data? So I'll go back to my embeddings here. And you can see that right off the top, we have all these different embedding space that's very diverse. The distribution of different butterflies, to maybe no surprise to us, is that butterflies can look very different, right, from one butterfly to another. In looking at here, it's kind of tough to see. If I was looking at just the total embedding space in general, it might be difficult for me to understand where my monarch butterflies are, where they're not. And so what we can do in FiftyOne is we can actually turn on and off different classes. So if I go over to my monarch butterfly, I can turn off just my monarch butterfly. And maybe the problem now has become much more clear to us as I can select my butterflies over here on the right. And we can see that these are all monarch butterflies, but we can see there's a distribution that's much farther from our other one, or this little cluster. And if I grab these clusters, lo and behold, I've grabbed 5 images. I mentioned I grabbed 5 synthetic images in my data set. And we can see that these butterflies, despite looking like all the other butterflies in our data set, our model no longer sees them as the same amount of butterflies, or doesn't see them as the same butterfly. There's this large gap between the two, and it's super easy for us when we use embeddings to see that our model is no longer seeing these as the typical monarch butterfly, and that we're now drifting our data unintentionally, right? We would want these clusters here to be moved over here and to stay with the rest of our monarch butterflies to bolster our data set. Instead, we've actually had the opposite problem here. And so once again, once I turn back on all my embeddings, it becomes obvious how these are hiding amongst the entire, it's like finding needles in the haystack sometimes of trying to find out that your model is, your data points are drifting within specific classes, not even as a whole data set. And if you weren't able to get this level of granularity into understanding your data set, then you wouldn't know if you're actually going to drift your model or hurt your model. So the main takeaway here is not to avoid GenAI or to not apply it to your computer vision data sets for augmentation. It's actually more that if you are going to be doing this, make sure you're taking into account things like embeddings of your models to understand the drift of your data set, to hope that your data that you're augmenting is always going to stay within the same distribution of your existing classes. If they're going to be moving somewhere, then now you're training to a different problem, and that's not really what we're trying to accomplish. So there are ways to help mitigate this, whether it's different types of prompts, maybe a level of in-painting, as well as trying to match other things such as resolution, the size of the images. But overall, as I keep on testing this problem, especially total image or totally synthetic images aren't quite there yet in terms of matching the exact distribution from such a simple prompt as a monarch butterfly, for instance. So hopefully this has been insightful for you. This has been clear enough. I hope it's a quick flash talk to get the point across. I'm going to answer some questions, and then I'm sure Preet's going to go into even more detail about all the awesome things that embeddings can do. This is just a nice, fun example, and hopefully it rings home to you guys to make sure you're always keeping an eye on your AI, making sure you're always able to explain what's going on, and that you're not actually hurting your problems by adding some new generative data sets and generative AI into your data set workflows.
Dan,
So
thank you. Great
yeah,
presentation. It's funny. I've been having like recurring dreams of butterflies, specifically monarch butterflies, and I've been seeing them everywhere. Did not expect to see them this morning in this talk. Thank you for that. There are some questions in the chat here. If you want to go ahead and pick a few that you want to answer, and then the rest you could take offline before we move into the final talk.
absolutely. So we have one that's asking that they worked on an AI model that detects LLM generated text. We use generative AI to generate text, which is used as a data set. Yeah, so this is not quite ready for something. I wouldn't say it's as robust enough to say that you can determine deep fakes or synthetic images, as in for sure 100% positive. But this is probably your best way to go about it if you compare and contrast, butterfly images to just synthetic butterfly images, and given a set of butterfly images, if you give me a new fake one and you tell me what type of butterfly it is and things along those lines, then I think that given the distance from the embedding space, you could be able to tell whether or not it's generated or not. But you can see that the monarch butterflies in whole don't jump out like enormously far from the rest of the distribution. Since they're still hiding amongst other butterflies, it's not so easy to say the problem, especially without labels, that, monarch butterflies, these ones are definitely gen pictures versus other ones. It's not quite ready there, but it would be interesting to explore that work, especially with a more robust embedding model that is built and trained to do this kind of task. So if we want to generate high quality and specific domain generated images, what do we do? Please help advise us. So there are ways you can help do it. Things like conditioning now is something that you can do. You can text prompt or image to image. There's also ways to generate things like depth maps or normal maps or on your images to get a more robust and more within distribution method. I can't name all those type of ways, but basically different forms of conditioning on your diffusion models, whether it's class-based or something else like a depth map, will allow you to keep more of the distribution intact, and you will kind of remove part of that data drift problem because the structure of your image is much more robust. There's some work that just came out of CBPR 2024 talking about this, that if you maintain the shape of the objects in your data set and you're only going to change things like the colors in a way that makes sense, that you're going to have a much more or less of a data drift problem from this. So haven't been able to read all those papers yet, but it's still very new in this field. It seems like I said, classes and depth maps, especially to condition your generative models on for images, is seeming to be the next step for us.
Awesome, Dan. You want to take one more question, and then we'll get into my presentation. Raphael is asking which software you're using. We'll talk about that next, Raphael. So
Awesome.
sit
Uh,
tight.
okay, Marcos, I pretty much answered that with the last one with conditioning. Uh, it will still detect. This isn't going to ruin your model, so that's a quick one. But the last one I like to answer is there a specific way to quantize the drifting of your model due to generative AI approach to increase the existing data? So is there a way to quantify exactly how we're looking at this? The answer is yes. The easiest and best way to do it is with embeddings. Exactly the way I just showed you is probably the number one way, right? Basically, as you add these new samples in, like these 5 pictures, we can calculate the distance in the embedding space from existing monarch butterflies here to the new added monarch butterflies. As long as this distance is within your acceptable threshold, that will be your go-to to quantify exactly how your images are doing it. You could even take this to the next level, uh, is doing the intermediate outputs of your model. So if you're able to determine at, either early or late stages of your model, embeddings are always going to be at the end, for instance. You can also get more insights where sometimes a lot of this is being seen at the highest levels of your model, saying like, oh, I've never seen this image before, essentially. And it gets all confused, but it gets kind of smoothed out by the end. The only other way to do it too is by doing things like evaluations, for instance, like if you train your model only on the original data points, how well does it detect on your existing images? That's a little bit of a not the best way in my head. I would use embedding space distance as my go-to. All that can be done here in FiftyOne. But yeah, embedding space distance is probably your best way, especially if you're using a really powerful embedding model. But I'll stop sharing. I'll answer any more questions if you guys message them in the Q&A in the chat. You'll just get an answer there. But I'm excited to move on to the next presentation and see what Harpreet has in store for us.